Okay, this is a continuation of the sample problems for exam 3 for Math 2415. We're at problem number 18. And we are asked to find the center of mass of a lambda bounded by the coordinate axis and the line x plus y equals 2 with the density function of x plus y. So let's look at the region here. There's the line x plus y equals 2. I think whether you go dy dx or dx dy doesn't really matter too much. And so it's just a little inner triangle here bounded by the x and y axis. So I chose dy dx. That means I would be going from a y of 0 to the line, which is 2 minus x, and then left to right on the x-axis from 0 to 2. And then we just integrate x plus y dy dx. So with respect to y, what's that going to give us? It's going to give us antiderivative of xy, then plus y squared over 2. Plug in 2 minus x, plug in 0, which the 0 will have no effect. So I'll plug in 2 minus x here, and just distributed the x right there to get 2x minus x squared. Here you have to FOIL out that binomial and then divide everything by 2, which will lead to this. And looks like that you can see the 2x terms will actually cancel. That's just convenient, helpful. And we actually have two like terms here of x squared. So basically a negative 1x squared and a positive 1/2 x squared would add together to be negative 1/2 x squared. And then 2 is just 2. Now you could have integrated it without the simplifying. Well, I certainly would have canceled the x's. But it makes it a little easier. Now we'll take this antiderivative with respect to x. Will be x cubed over 3, so it makes it negative 1/6 x cubed. And 2 will be 2x from 0 to 2. Plug in 2, plug in 0, and you'll get 8/3. Now we have to find these two things called the moments here, the my moment and the mx moment, which are both going to be divided by the mass. Okay, it looks like I just kind of skipped all the arithmetic steps here. Hopefully, what I showed you here up on the mass part of it will kind of give you a guideline. It's going to be a little bit different, but I just didn't go through all the integration, which is not really that complicated. It's just basic algebraic terms, but I didn't show all the work. But the setup's important here because the my moment, the region of integration will be the same for all three of these double integrals. So once you have it set up the first time, you can use it for the next two. So it's always, for the my moment, it's always x times your density function. So we're integrating x squared plus xy. And the antiderivative in respect to y would be x squared y right here. And then the antiderivative y would be 1/2 x squared with the x there. So I stopped right here, meaning you're about to plug in the 2 minus x and the 0 into here. Which frankly at this point, if you plug the 2 minus x in there and you reduce it down to a variable of x, you can use the numerical integration in a TI-84 or something like that, you know. The only calculators I don't allow are the ones that can do the algebraic integration. But I say numerical, I mean that it can integrate definite integrals, single definite integrals. That's okay. And so you can put the 2 minus x in there and combine all that, then you can just do it from 0 to 2, and you'll get 2. And then the mx moment means you multiply y times that function. And then so xy with respect to y will have an antiderivative of xy squared over 2. And then y squared with respect to y will be 1/3 y cubed. Then you plug in the 2 minus x and the 0. And just coincidentally, it works out to be 2 again. And the center of mass, the x component, also, or x bar component, it's known as, but it's the x component, will be my divided by m. And the y component will be mx divided by m. Now, you would have got lucky on this problem, but I wouldn't rely on luck, meaning if you got the mx and the my, reversed, just because they happen to be the same number. But let's don't do that. Let's make sure we get the my first. So 2 divided by 8/3, and 2 divided by 8/3 gives you 3/4, 3/4. Now it's very important that your answer fits somewhere in your shaded region of integration. And so you can just take a quick look at your shading here and see that, yeah, so the point 3/4, 3/4, might be somewhere right in there. So yeah, it's in your region. So I guess the point I'm trying to make, let's say if you came up with an answer of 3, 1. Well, 3, 1 would be out here somewhere. It'd be out of that region. So that means there's no chance that 3, 1 could be correct. The 1 could be correct, but not the 3. So we take a quick peek at that to make sure it fits in there. So that's good. And all right, so there's your center of mass. So here's one that's just asking for the mass only. Yeah, now one thing, keep in mind you're doing integration is, there are some problems that'll tell you, it'll tell you, for example, to convert to polar coordinates, this, that, and the other. Always keep in mind if you think polar coordinates is the proper way to go, you don't have to be given permission to use polar coordinates. Your goal is to always do this the easiest way possible. So like, for example, this problem says nothing about polar coordinates, but it is by far the obvious way to go here. 2 reasons. Your region of integration is a circle, and then that x squared plus y squared of the density function makes it perfect for polar. I didn't sketch the region, but I'll just say it verbally. X squared plus y squared equals 81. No restrictions on x and y. So it would be a full circle, radius 9. Full circle means you're going to go from 0 to 2 pi in your outer limits for theta. And then the radius will be 0 to 9. Now the r squared here comes from that x squared plus y squared for the density function. And then, of course, anytime that you use polar, you always have that r d theta. So really all we're doing here is, now the integral's pretty easy. So we're integrating r cubed, which will be 1/4 r to the 4th. Put in 9, put in 0, 9 to the 4th is 65, 61. And then we're integrating d theta. There's no thetas there, so it just produces a theta. So from 0 to 2 pi gives me 65, 61 pi over 2. And there we go. So that was important just to realize that, polar coordinates can be used whenever you feel like they need to be used. Now, of course, you would not want to introduce polar coordinates all the time, because there are some integrals where it would be inefficient to do it that way, and maybe even impossible. Yeah, like here's another problem that's pretty much set up perfectly for polar. We're going to find the surface area. And the surface area is the double integral across your region of the function, the square root of 1 plus fx or z. I have them as zx and zy. Those are just the partials. So I'll say it this way. I may have it, the notes, I think it's written as fx and fy. But it's 1 plus zx, the x partial squared, plus the y partial squared. So here's the function for z. So the x partial would be negative 2x. The y partial would be negative 2y. So squared, that would be a 4x squared plus 4y squared. It's a square root of all that. So that certainly does not look fun to integrate in rectangular form. And it would not be pleasant, if even possible. But let's take a look. Now think of the paraboloid. We're looking at the xy plane to get our region of integration, meaning that z is going to be circle. So that paraboloid is, I think I've got lots of paraboloids in my notes, but so it's just, I'll kind of sketch this real quick, like it'll be like that. That's not very good because I'm using freehand here without like that. Anyway, so it's a circular base down here on the xy plane. So we need, hold I'm not sure if I'm helping any with this or not, but all right. Anyway, so that's what you're looking at. So essentially you're looking at a circle with radius 5, because square root of 25, and nothing restricting it. Well, it's above the xy plane, but I mean nothing restricting the values on x and y. So we'll use that full circle. Sometimes it may say, you know, like in the first octant or something, meaning x and y are both positive. So you would go from 0 to pi over 2. This one, full circle, 0 to 2 pi. Got to be real careful with that, because obviously that can, you know, greatly affect your answer. You know, even if you do everything else right, you have to get that outside limits for theta correct. The r shouldn't be too difficult to get those correct. So 20 radius is 5, so it's going to go from 0 to 5. So the square root of 1 plus 4x squared plus 4y squared in polar converts to 1 plus 4r squared, the square root of that. So we have this right here, and then our r that comes in there, r dr d theta. Now, of course, that r is very important for us to even be able to solve this integral reasonably. It could be done without it, but I would never ask a problem that you would have to do that, because it would involve trig substitution or using an integration formula or something like that, because it's not that easy to integrate that by itself. But the r with it makes it, kind of takes it back to a Cal 1 type integral. It's just basic substitution. So you let u equal 1 plus 4r squared, du equals 8r dr. Put in 5, 1 plus 4 times 5 squared is 101. Put in 0, you get 1. Always like changing my limits of integration. So I'm going to have u to the 1/2 du d theta. And we're going from 1 to 101. And then still 0 to 2 pi. And the 1/8 comes from dividing both sides. I just didn't show it, but you have to divide both sides by 8, so it makes it 1/8 du. So I just brought the 1/8 to the outside. So the antiderivative of u to the 1/2 will be 2/3 u to the 3/2. So I have a 1/8 and a 2/3. That'll turn into 1 over 12. Now we put in 101 and we put in 1. So we have 101 to the 3/2 minus 1 to the 3/2. 1 to the 3/2 is just 1. So that's why I don't have the 3/2 here, because it's just 1. So it's, you know, you're going to have it's not uncommon, because this formula has radicals in it, that you're going to have a radical in the answer. So 101 to the 3/2 is mathematically acceptable, but a lot of times when you're picking multiple choice answers, though, it will rewrite it as this. So this is the same. 101 to the 3/2 is the same as 101 times the square root of 101. And then now for the last integral, all you're doing is bringing in, so d theta will be theta. So you're bringing a 2 pi down. So 2 pi times 1 over 12, that makes the pi over 6 out here. And there we go. There we have it. Let me see. Look at the answers. Yeah, see, it broke that radical down. That's why I did that. All right, so that's not too bad. Just use substitution. Here's another surface area. A plane lying in the first octant. So to get our equation, we have to rearrange this as z as a function of x and y, so we can come up with that formula, 1 plus the x partial squared plus the y partial squared. So you solve that for z, so you have z equals 16 minus 3x minus 4y. The x partial will be negative 3, the y partial will be negative 4. So we have the square root of 1 plus negative 3 squared plus negative 4 squared is the square root of 26. Well, that's kind of nice, because that'll make this part not too complicated. However, now the region of integration, we treat it as it's on the xy plane, just like we did even with that last one, paraboloid, is you basically zero out the z. So you're on the xy plane, so you don't really need a picture of this. Just zero out the z, and you're left with this equation, which means you essentially have a triangle when it's on the xy plane. And for some reason, I chose, it makes really no difference, I don't think. I chose dx dy this time instead of dy dx. Not sure why. Maybe because I wanted to have a whole number 4 out there on the outside. I don't know. But anyway, so I solve for x in terms of y. So x will go from 0 to 1/3 times 16 minus 4y. And then to get the y, you go ahead and just zero out the x. And you're left with 4y equals 16. So y will go from 0 to 4. So the square root of 26 can just be brought out here, and then the dx, antiderivative of dx is just x, which will bring this part out. So what I did is the 1/3, I just brought that out with the square root of 26. And then I'm left with 16 minus 4y. So let's do that antiderivative with respect to y. We have 16y minus 2y squared, going from 0 to 4, and it gives me square root of 26 over 3 times 64 minus 32, which gives me 32 over 3 square root of 26. Okay. Number 22 is another surface area. So this is one of the ones where it gives you the vertices points and you have to come up with the equation of the line, but that's not too difficult. However, you have to pay attention carefully what's the correct shaded region here. So you see it's bounded by 0, 0, 0, 4, and 4, 4. So you kind of connect all those. I don't really didn't need that bottom line there. That's okay. So it's definitely that upper triangle based on the points that were given. And the line's going to be y equals x. It's got a slope of 1. In fact, this point right out here is going to be 4. Yeah, the 4, 4, 0, 0. Slope is 1. Y-intercept 0. So it's just y equals x. So that'll be important for our limits of integration. Now, so we have z equals y squared, so we need the partials. Well, there's no x variable there, so the x partial will be 0, but the y partial will be 2y. So we're going to have the square root of 1 plus 2y squared, so it's 1 plus 4y squared. So that's what we're integrating, dx dy. Now, dx dy is kind of important for this one, is because I don't want dy first, because then it comes into one of those square root integrals that I was mentioning in the last problem that can be quite complicated. So this one, I want the dx first, because it's going to bring that y in we need for the u substitution. So it would have been so this one, the order does make a huge difference. A lot of times it doesn't. Here it does. So going left to right, so if y equals x, of course, that's the same thing as saying x equals y. So we're going from 0 to y, and then 0 to 4. So 0 to y, 0 to 4, dx makes that x, throws that y in there, and now we're set up perfectly for u substitution. Yeah, it would have been kind of a mess the other way. So 1 plus 4y squared, which makes the du be 8y dy, so divide both sides by 8. That gives you 1/8 on the outside. Plug in 4, plug in 0. I'm changing my limits of integration. 1 plus 4 times 4 squared is 65. 1 plus 0 is 1. So it's 1/8, 1 to 65, u to the 1/2 du. So the antiderivative of u to the 1/2 will be 2/3 u to the 3/2. 1/8 times 2/3 is 1/12, and then you have 65 to the 3/2 minus 1 to the 3/2, which 1 to the 3/2 is 1. And all right, this one's kind of interesting on the answer choices. We had a problem like this recently where it split it up into radicals. This one did not. In other words, it does not have 65 times the square root of 65 as the answer. It could have, but it did not. So sometimes it might just have the 3/2 power, or it might break it up, on the radicals. Just go by whatever the answer choices do. On a handwritten exam, I would not care which way it was written. Both would be acceptable. All right, number 23, 23. We're now getting into some triple integrals. This could be fun. Now I put a little note here. Okay, so I'm mentioning that this kind of could sort of be polar looking, especially because of this part right here. But I've never actually tried it in polar, but this is not too... I know there's a lot of steps there. A lot of steps doesn't mean the problem is hard. It just means it could be tedious. But this... well, technically when I say polar, it's really cylindrical coordinates when it's 3 dimensions. Anyway. Maybe one of these days I'll work this out just to show people. Oh, and there I did. Every time I think I'm coming up with a new idea, I've already done it. All right, well, I guess you can decide for yourself. Then maybe it's equally as, whatever. I guess it's, yeah. I don't know. So let's just kind of look at this. So we'll look at the rectangular setup here, and, I'll just kind of fly through this a little bit. The integration's not hard to actually do. So I don't, there we go. So it's already set up, so nothing for us to have to, draw or set up a region of integration. So 5x, 10y, antiderivative with respect to x will be 5x, x squared plus 10yx, or 10xy. Put the radical in there. And because you're squaring the square root right here, there's no power, so it just goes, the radical goes away. But here it is to the 1/2 power. But here's what I was talking about. The first integral is just going to be basic antiderivative rules, nothing tricky. Integrate them by term because there's no exponent here. But this is what I was talking about, why polar is not, or cylindrical is not necessary, because U substitution now with that y right there makes that pretty straightforward. So here's the U substitution for this part. So it looks like I kind of just broke them up in two just to separate them, just to keep the first part away from the second part. Because the first part's pretty straightforward. Second part's U substitution, not too difficult. And then I got 625 by adding them together. The two individual integrals. And then here it is in cylindrical coordinates. Cylindrical coordinates, remember, are just a polar with a z. So it has that, instead of r dr d theta, it's r dz dr d theta, but it's same kind of concept. So x and y have to be written as r cos theta, r sine theta. And then, now how do I know it's 0 to pi over 2? It's because if you graph this with both of these limits right here being 0, forget the first one here, but pretending like we're just in the xy plane right now. Both of those being 0, that's the first quadrant. So it's just going from 0 to pi over 2. To go further than that, there would have to have been some negatives down there. Like if that would have been -5 to 5 and this would have been 0, then it would have been 0 to pi. All right, so maybe I don't know. You can make a good case for this one not being as bad this way if you want to. I don't know. This one, I think, I can say that you can have your own opinion on whichever one you like better. Sometimes if I tell you which way is clearly better, but I'll kind of skip all the steps here. It's pretty straightforward. Once you get it set up here, then, put the r's in there, and then integrate the r's. Cosine and sine will stay there the first time, and you'll get 5r cubed over 3, 10r cubed over 3. And then put in 5, put in 0. So you get a 625 over 3, a 1250 over 3. Integrate the antiderivative of cosine will be sine. The antiderivative of sine will be negative cosine. So there's the negative. Put in pi over 2, put in 0. You get a couple of 0 terms, but you get a couple of the non-zero terms. Add those together. You get 625. So answers match. That's good. So that problem's kind of interesting, I guess, because usually one way is clearly better than the other when it comes to polar or cylindrical versus rectangular. Anyway, number 24. Okay, this is nothing. This is just a straightforward, basic triple integral here. It's just can you do the process. Nothing tricky or to be concerned about. So the first one here is dx. So the antiderivative of dx would just be x. So you put in z, you put in 3. So you'll have yz times z minus 3. Now the next step, I distributed and integrated at the same time. So that's going to be yz squared with respect to z, which makes that yz cubed over 3. And this is negative 3yz, which makes it negative 3yz squared over 2. So it kind of did a couple steps at once. So you don't have to do that, obviously. Put in y squared, put in negative 1. And that's going to give you this stuff right here. There are a couple of like terms you can combine together. These two right here, they're both y's. It's kind of tricky with all those negatives. But this negative out here will change both of those to positive. So basically it's y over 3 plus 3y over 2. Common denominator gives you 11 pi over 6. And then it's just basic antiderivative stuff from here. Power rules for all of these. 3 separate power rules. Blah, blah, blah. Put in 2, put in 0. You get negative 5/3. Oh, which is answer A. Keep in mind that, when you're evaluating a double or triple integral, that, the answer can be, negative, positive, 0, whatever. Where you have to be concerned is if you're doing a problem that's evaluating something like area, volume, surface area or volume, or something that's a measurement, your answer needs to be positive for obvious reasons. But if somebody just slaps down an integral problem from nowhere, there's nothing wrong with the answer being negative. Evaluate a triple integral where we have to set this up. So I like to try to start dz, dy, dx, because these, without pictures, you can get a little tricky. But this one's not too bad. Something more complicated, I would certainly give you like a picture or something. But this one, so you see you got z equals 0, then you got an equation with y and z. So I would start with dz, and I'd go dz, dy, dx. That means z can be any combination of variables y and x. So if you just take y plus z equals 2, z will equal 2 minus y. So z is going from 0 to 2 minus y, like that. And then we essentially, if you treat z as 0 right here, y is going to have a maximum value of 2, and then y is going to go from 0 to that 2 right there. And then x will go clearly from 0 to 1 based on those results. So All right, so it's pretty straightforward here. Antiderivative of z respect to z would be 1/2 z squared. Put in 2 minus y, put in 0, you get 2 minus y squared. You could use u substitution, and I would certainly use u substitution anything power 3 or higher. But squaring a binomial, if you do it if you want to, but you can make a good case just for multiplying it out, which is what I just did. I said, square a binomial, I'll skip the substitution and just FOIL it out. And I get this, 4 minus 4y plus y squared. That's going to be dy dx, so I'll take the antiderivative of that respect to y. Will give me 4y minus 2y squared plus 1/3 y cubed. From 0 to 2. So 4 times 2 is 8, minus 2y squared, 2 squared is 8. 1/3, 2 cubed is 8/3. Still have the 1/2 there. And I have 1/2 times 8/3, just 8/3 dx. So the antiderivative of dx, of course, is just x. And 1, 0 just makes out a 1. So basically the answer is just 1/2 times 8/3, which is 4/3. All right, number 26. Rewriting the integral. Okay, so it's this is going to be an equation of a plane. So this could have been asked two different ways. It could have just given you the equation of a plane and said write it in a specific order. But here it's kind of interesting because they're giving you the integral already set up and then switching it to another order. So to do that is we have to recreate the original equation of the plane, which is not that difficult. Since we know that z is going from 0 to this value right here, 4 times all that. So we know that z goes up to this value. So what we can do is take this equation and essentially solve it it's technically a plane equation, but I want to get everything back in terms of the basic form where it's just x, y, and z equals a number. So I divided by 4, brought it as z over 4 right here, and left it equal to, so I brought these two negative terms over and made them positive, left it set equal to 1 right here, and then I wanted to clear out the denominator. So 40 is the least common multiple of 4, 5, and 8. And that gives me 5x plus 8y plus 10z equals 40. So, yeah, the problem would have been easier if they would have given it that from the beginning and said, then make it in a certain order, but it's not that hard to come up with it. So once we have that original equation of the plane like this, no problem, then we can come up with the rest of any of the other 5 orders, other than the first one that's already given. So let's see what it wants. It wants dx, dy, dz. Okay. That means we have to solve for x first. So we take this equation of the plane, solve it for x right here. So brought everything over, divided by 5, and x will equal 8 times 1 minus y over 5 minus z over 4, which I'll go ahead and point it out here in the answer. Coincidentally, that's the only one that has the right, of the 4 that has the right answer here for this one. But, don't assume that. Obviously, another answer could have had this same part, so you would have to go to the next step. But we do have, but in this particular, because of the answers, we really do have the answer. But we're going to keep going here. We're going to see how this is done properly. So there's the x. So what you do, anytime that you solve for a variable, you essentially can zero out that variable and move on to the next one. Because now we're only working in the yz plane. So the yz plane means x is 0. So I just let x equal 0, which I don't have to do it right here. I can do it back from the original equation. I can zero it out right there. And that's what's giving me the 8y plus 10z equals 40. And I'm solving for y because that's the next order from inside to out. Solving for the y. So 8y equals 40 minus 10z. Divide both sides by 8, so we get this result. And then it reduces. So it's 5 minus 5/4 z. I factored out a 5 right there just to make it match what the answer looked like. So there's the second part of this. Now in terms of z, the outside limits of integration are always numerical. So that means you can work with what we already have, or you can go right back up to this one again and just zero out the x, zero out the y, solve this. 10z equals 40. And that's pretty much means 4. So you're going to go from 0 to 4 for z. So that gives us the 0 to 4 right here, and then that will be your answer. Number 27. We're going to evaluate triple integral given by the following regions. And let's see what we have here. We've got z equals 0 below, z equals y above, and then on the side by the parabolic cylinder, y equals 9 minus x squared. So this one, and then the function, and it's y dv, so the volume region. So we're integrating the function y, that has to go there. So I think dz, dy, dx will work out well. dz first, for sure, because we know we're going from z equals 0 to z equals y, so that makes that one easy to set up. And then y equals 9 minus x squared will go from 0, basically since the z is 0 here, the y would also be 0 at the minimum value. So we're going from 0 to 9 minus x squared, but the x doesn't have any restrictions, so it can go from negative 3 to 3. All right, so we integrate the y and then dz, which brings a y in there. So it gives me y squared dy dx, which makes this 1/3 y cubed, 9 minus x squared dx. And that makes, when you bring the 9 minus x squared in there, that gives you 9 minus x squared cubed. Now here's what I'm mentioning. There's no way I would ask you to cube a binomial on the test, but I just kind of wanted to leave the problem there, mainly just kind of for the setup purposes of it. So it didn't quite work out the one that I would expect you to do, but I went ahead and finished it. I cubed it out and got this. Yeah, the cubing it would have been a pain, but once it's cubed out though, it's easy to integrate term by term. Yeah, even though that wouldn't be hard to do, obviously with the definite integral capabilities on a calculator, but still, I'd rather have problems that they don't have to be done by that feature in the calculator. They can still be done manually, in case someone's not using one or something. So makes it fair for everybody. All right, this one might have been a nice one to have a picture of, but I think it's doable without the picture. All right. So let's jump down here to 28. Evaluate this problem by triple integration. Yeah, this, and I put a little note here on this, that I decided at some point after doing this that it was too much hassle to work all this out. And also I discovered that there's a formula to find when you have a plane shape like that. It's called a tetrahedron. Yeah, I believe the formula is something like 1/3 times the area of the base times the height, or something like that. But anyway, let's just look at the setup for it mainly. So this did this last problem, not the last one, a couple problems ago. Yeah, where you had to rearrange it from here. This one we're actually starting with the equation without having to come up with it. Let's see. So here's the equation, and yeah, now this one is not specifying an order, so we'll just pretend like it was dz, dy, dx. You know, it'd probably tell you what order it wants it in. So you solve for z in terms of everything else, which gives you 1/2 times 12 minus 4x minus 3y. Then you get rid of the y. the z, zero out the z. And let's see what you have. That will give you 4x plus 3y equals 12, which gives you 1/3 times 12 minus 4x. And then you get, for x, you get rid of the y and the z. So you have 4x equals 12, and you have 0 to 3. Like this, like I'm saying, this problem's not mathematically complicated, but it's just kind of tedious working out all the terms here. But let's just focus on the setup, and I'm not going to ask you to do this to work this one out on a test with all the steps and everything. But yeah, after I discovered that formula, I kind of said there's kind of, nothing wrong with using calculus to sort of establish that formulas work, but this one's maybe a bit too much. But for example, I'll see if I can find room for a little sketch here for a second. Let's see. Yeah, I'll do it right above it. So put the axis here. Sketch is not going to look good, but it's going to get you the points of intercept here, and let's see. And the x-intercept will be 3. Y-intercept will be 4. And the z-intercept will be 6. All right, let's see. So the area of that base, area of a triangle, is 1/2 times base times height. So it's 1/2 times 4 times 3, which is 6. And then the formula is 1/3 times that area of the base times the height, which is 6. So it's 1/3 times 6 times 6, which equals 12, which is exactly what the calculus bears out to be, is 12 here. It's exactly what the integral produces, is 12. All right, let's see what's next here. Number 29. Going to find the volume of a region inside a cylinder. So it's below a sphere, inside the cylinder. So you're looking at potentially spherical coordinates or cylindrical coordinates. Let me see if I did this one in spherical. Looks like I didn't. Now, a lot of times, it looks like it would be spherical because of the region is a sphere. But what I did is did it in cylindrical. It didn't work out this bad, so I didn't even try it in spherical, mainly because the region was a cylinder. That made it work better, I think, than it would have been in spherical. So we have the height, basically, is going to be solving this equation for z. So, and x squared plus y squared is r squared. So r squared plus z squared is 81. So z equals the square root of 81 minus r squared. So integrating it in, looks like I did polar, but if I would have done r dz dr d theta, z would have gone from 0 to this part right here, 81 minus r squared to the 1/2. So then this is almost like this is the second step of the cylindrical, where it's just dropping that value in for the z. Now we have our standard r there. And this is good because the cylinder region of integration, I think it makes this easier. So there's nothing restricting the entire cylinder. So it's going to go from 0 to 8, and then 0 to 2 pi. This will be a U substitution integral. You put in 8 here, you get 81 minus 64, which is 17. Put in 0, you get 81. And I have a negative 2r dr, so I have a negative 1/2 that will come out from both sides. 0 to 2 pi, 81 on bottom, 17 on top. U to the 1/2 du d theta. That gives me, that'll be 2/3 u to the 3/2. So, yep, 2/3 u to the 3/2. So 2/3 from that power rule times this 1/2 would make it 1/3. Now here's why the negative went away, though, is because I reversed my limits of integration using that property from Cal 1. So I changed them over. You don't have to do that, but I changed them over, so that's what got rid of the negative right here. Flip them around, and that's why it's positive. So 2/3 times this 1/2 is 1/3. And that gives me 81 to the 3/2 happens to be a whole number because the square root of 81 is 9. So it's 729, but this one is not. So it's 17 to the 3/2 with a 1/3 there. And then the d theta just produces a theta, which just produces a 2 pi in there, 0 to 2 pi. So it's 2 pi over 3, 729 minus 17 to the 3/2, which you can see right there. Okay. Number 30. This is a region that's inside the sphere and outside the cylinder. So the similar to the last problem was inside the cylinder and below the sphere. This one is, and these kind of problems are in my notes, so if you want to see some visuals of what that looks like. So basically it's a cylinder inside of a sphere. This time we're trying to find the volume outside that cylinder, but still in the sphere. So this one, really the only difference is R. Everything else is pretty much the same. So instead of going from before, we were going at a starting point of radius of 0 to the edge of the cylinder, which is 8. But now we're going from the cylinder to the sphere. So it's the square root of 64 to the square root of 81. So it's going from 8 to 9. Okay, so the rest of this is pretty much all the same here. So I did the change the limits of integration. I flipped them over again to kill the negative. There's the 1/3 again. So this one you end up with 2 pi over 3 times 17 to the 3/2. So the only change in that problem was the limits of integration for the r. All right, so based on that other problem, that made this one easy to set up. So you see everything, I did the same as the thing I did before. Same function we're integrating. So it's very, very similar to 29, except for that, except for r. Number 31. Region enclosed by the cylinder. And the plane z equals 0 and x plus y equals plus z equals 18. So we've got a sphere cutting through that plane, and we're trying to find the volume under that plane, but inside the cylinder. I think this is one that on an exam I would provide the graph. If I had one like this, I would provide a picture of it for you to see. Well, this is a pretty lousy freehand sketch, but just want to give you an idea. So the pink is essentially the volume you're trying to find here, and there's the plane cutting through. So it's the amount of volume that's inside that cylinder, but under that plane that's cutting through. So let's see what we have here. So I'm solving for, so we're doing cylindrical coordinates. So I'm solving for z in terms of x and y. Now we don't have the benefit, like if, for example, if this was 18 minus x squared minus y squared, then we would have 18 minus r squared. We don't have that benefit. X is r cos theta, y is r sine theta. So we're going to go from 0 to 18 minus r cos theta minus r sine theta. And we're just integrating r dz dr d theta. And the cylinder will go from 0 to 9, 0 to 2 pi. So that's not too bad. I've seen easier ones, you know. Like I said, the 18 minus r squared would have been easier. Just have to be careful with the cosine and the sine here. Now, I did 2 steps at once again here. I distributed the r and took the antiderivative with respect to r in the same step. So 18r would be 9r squared. Negative r squared cos theta. Negative r squared cos theta would be negative r cubed over 3 cos theta. And same thing with the r sine theta. So we don't integrate the trig functions yet. We put in 9, we put in 0. And that's going to give me then 9 times 9 squared is 729. 9 cubed divided by 3 is 243. Once for both of these. So now we integrate with respect to theta. And the antiderivative of negative cos theta will be negative sine theta. And the antiderivative of negative sine theta will be positive cos theta. So we put in 2 pi, we put in 0. So 2 pi for this theta gives me 1458 pi. Sine of 2 pi is 0. Cosine of 2 pi is 1. So that's going to give me 243. Then when I put in 0 here, that's a 0. The second one's a 0. But this is not a 0. 243 cos of 0 would be 243. So they end up canceling anyway. the 243's cancel, but it's not 0. And you end up with 1458 pi. All right, get rid of this ugly drawing here. Number 32. So this one is already in spherical coordinates, so we are just manually integrating it. In other words, nothing needs to be set up or anything. And they're using, well, they're not, I guess that's just some way they're printing out the phi that we normally see in our book. Don't let that bother you, but I mean, I guess it's, so they're using a different looking variable. Whatever that Greek letter is, I don't know what that Greek letter is. That's okay. You see, I went ahead and just changed it to the phi that we're used to. So we're integrating respect to row the first time. And don't forget this kind of problem, just like you would do for cylindrical or polar, don't put in, like for this one, don't put in the rho squared sine phi that you put. That's only when you're converting from rectangular to spherical. If you're just integrating a given function already in the form, you don't convert it. People have asked me that before or whatever. So like, in other words, if you're integrating something that's just already in polar coordinates, nothing to set up or whatever, you don't put in that extra r. But this one, yeah, so if you're just integrating in its natural form, you don't convert it or anything like that. So people will ask me, do I have to put that in there? No. So it'll be 1/4 rho to the 4th, 5 sec theta, 4 sec theta. So we have, let's see. So you're going to have 5 sec to the 5 to the 4th. That's 620. So you have basically 625 secant 4 minus 256 secant 4. So they're both secant 4th, so they're like terms. So that's how I got the 369. So 625 sec 4 minus 256 sec 4 gives me 369 sec 4. So that's where this 369 is coming from, and there's your sec 4. Well, we got all kinds of mixed trig functions here, but as you would probably suspect, we're going to need to convert that secant to cosine, obviously, to get this in a form that we can integrate. And since secant is 1 over cosine, secant to the 4th would be 1 over cosine to the 4th, or cosine to the negative 4. So secant to the 4 is the same thing as cosine to the negative 4. So cos negative 4 times cos to the 1st gives me cos negative 3 times sine. Okay, so after we simplified all that mess, it boils down here to a nice U substitution. So we're okay here. Nobody's hurt. So if U is cos theta, du will be negative cos. I keep saying theta. Excuse me, phi. Negative sine. There are no thetas here. But be careful when you're looking at problems because they could have phi and theta both in the same problem. Negative sine phi d phi. All right. So that fits well, except we're going to have to bring a negative outside there with that 369 over 4. And changing the limits of integration. I put in pi over 3. Cosine of pi over 3 is 1/2. Cosine of 0 is 1. So I have 1/2 on top, 1 on bottom. Now, a lot of problems I've done, I didn't do it in this problem, but I want to at least mention it. I don't know why I didn't, but it's not wrong. But I could have flipped the 1 and the 1/2 and got rid of that negative out there if I wanted to. That would have been correct. But I think the reason why I didn't is because I saw what was about to happen, is that I knew that the u to the negative 3 is going to also produce a negative. So that's probably why I left it alone. But I just wanted to mention that. So the u to the negative 3 is going to be u to the negative 2 over negative 2, and then those two negatives just cancel anyway. So you have 369 over 8, u to the negative 2, or 1 over u squared, however you want to look at it. Well, 1 over 1/2 squared is 1 over 1/4, which is 4. 1 over 1 will be 1. So you essentially have 369 over 8 times 3 times pi over 2. And all that combines together to be 1107 over 16 pi. So we have 1107 over 16 pi. Number 33. Region bounded by a sphere and a cone. I would probably give you a picture of this, but this would be a good thing to know, because instead of having to go there's a lot of trouble to try to solve for it, I did it in my notes. But it's always true, so you wouldn't have to really solve for it at any, no matter what the size of the sphere is. The sphere and the cone are going to intersect always at pi over 4. Let's see if I have a picture of one to show you. Here's the page from the notes that I actually solved for the pi over 4, but it's pi over 4 regardless of the size of the sphere. The cone would keep expanding even if the sphere expanded, and it's still going to hit at pi over 4, no matter what. Now, the limits of integration, they're going to be different than what's in this picture. For phi, remember, phi means you're coming down from the z-axis. You're coming down from the top. So let me go back to the problem here for a second and see what we have. Above by the sphere and below by the cone. So unlike the one that's in my notes, we were figuring out the volume outside the cone. This is inside the cone, meaning we're starting at the top, which would be a value of 0 for phi, and as you come down, it hits there at pi over 4. That's why it's 0 to pi over 4. This example was not, because we were outside the cone, so it was pi over 4 to pi over 2. So in case you were looking at the notes and you were confused by that, that's the reason, because this problem here, we are inside the cone. And then theta would just go 0 to 2 pi. And then sphere, the radius, of course, of 36. Square root of 36 would be 6. So this works out really well. Spherical coordinates, no variables. All the integrals are going to be numerical. And then here's our standard rho squared sine phi that has to go in there when you're converting from rectangular to spherical. So it's rho squared sine phi, d phi, d rho, d phi, d theta. So this one, the antiderivative of rho squared, I kind of didn't show that, but I'll explain it verbally, is 1/3 rho cubed. When you put 6 in there, that's 216. 1/3 of 216 is 72. So that's where that came from. Now the next one, we're going to take the antiderivative sine of phi respect to phi. That'll be negative cosine. So still with the 72 out there. And I reverse the limits of integration to get rid of that negative. So I put 0 on top, pi over 4 on bottom. So now it's cos phi from 0 to pi over 4. Cos of 0 is 1. Cos of pi over 4 is root 2 over 2. With 72 in front. And now we have 0 to 2 pi of d theta, which produces a theta, which gives us 144 pi. And I got a comment, whatever. I was just trying to clean it up to make it look like, that answer. You could obviously check it, you could take your answer and make it decimal and see if it matches, the same decimal. But yeah, so I just got a common denominator and made it 2 minus root 2 all over 2. Then that 2 goes into 144 and reduces to, makes it 72. So it's 72 pi 2 minus root 2. Number 34, it's telling you spherical coordinates. This one's not too bad. Since x squared plus y squared plus z squared equals rho squared, that means the square root of it would just be rho right here. And then our standard rho squared sine phi, that has to go in there. It's a solid ball, meaning a sphere, of radius 4 centered at the origin. So 0 to 4 would be the radius. Phi would go from 0 to pi. Recall that you can't go more than 0 to pi for phi. That's in my notes, that section. But theta goes all the way from 0 to 2 pi. Yep, so 0 to pi is the maximum for phi. All right, this is going to be pretty easy. So that's going to be pi rho cubed, and you multiply them together, so it's 1/4 rho to the 4th. So I just plug the 4 right in there, so it's 1/4 4 to the 4th, which will be 64. And now we have to integrate sine phi, which is negative cos phi. Pi and 0, so it looks like I didn't reverse the limits of integration for this one. I could have, but it's okay. So cos of pi is -1. Probably would have been easier. Maybe I'll just do it sort of mentally here and reverse it. But yeah, let me do it that way. Cos of 0 would be 1. Cos of pi would be -1. So if you reverse these and get rid of the negative, you have 1 minus a -1, which makes 2. Times that 64 on the outside gives you 128. And then now you have 0 to 2 pi d theta. So that just brings in a 2 pi, and that gives you 256 pi. And we're done with that one.